Hello everyone, welcome back to my YouTube channel. So today we are going to solve day 12 problem of this month on LeetCode. Before starting, if you guys haven't subscribed my YouTube channel yet, then please go ahead and subscribe it. Now without any delay, let's get started with today's problem. Problem number 2529. Maximum count of positive integer and negative integer. Okay, so let's read the problem statement first. Okay, and I'm going to teach binary search algorithm as part of this problem. Okay, that is very important for your interview preparation. Okay, so this question is important. Okay, in that perspective. Okay, so let's read the problem statement first. So we have given an array nums sorted in non-decreasing order. Okay, so this is given to us, right, that our array is sorted in increasing order, right? Our array is already sorted, right? Then we have to return the maximum between the number of positive integers and the number of negative integers. Okay, in other words, if the number of positive integers in nums is pos, okay, this variable, and the number of negative integers is neg, okay, negative, okay, then return the maximum of this pos and this neg. Okay, note that 0 is neither positive nor negative. Okay, so this problem statement is very easy, right? This problem itself is very easy, right? If we want to solve this in of and time complexity, then it is very easy for you guys, right? So here, see this example number 1. So here in while solving the problem in of and time complexity, so what you are guys are going to do here, so you will take one pointer right at this position, and you will count that if this number is less than 0. Okay, if the number is less than 0, then you are going to increment the count of this to 1. Okay, and this number is also less than 1. Okay, so you are going to increment the count to 2. Okay, of this one. Then this number is also less than 0, then you are going to increment the count of this negative to 3. Okay, then you reach to this index, then you see that this number is greater than 0. Okay, so then you are going to increment the count of this pos to 1. Then you move here, then you are going to increment the pos of to 2. Then you move here to 3, then you are going to increment the pos of 3. Now among them, this negative and positive both are 3 3. Okay, so we have to turn the max among these two, so max is 3 only, so 3 is my output. So in this case, I am moving over all the indexes, right, one by one. Okay, so if the length is n, so I am checking all the n indexes, right, one by one, and checking if the number is less than 0 or greater than 0. Okay, if it is less than 0, I am incrementing the count of this, and if it is greater than 0, I am incrementing the count of this, and in the end I am returning the max, right? So for this case, the time complexity is of n. Okay, this is very easy then. Okay, now what if I tell you guys to solve this problem in of log n time complexity? Then what you guys are going to do? Okay, that is the real question here. Can you solve this problem in of log of n time complexity? Okay, so here, yes, we can solve this in log of n time complexity. How? Why? See, this is given in our problem statement that our array is already sorted. Okay, so this is the first property of binary search algorithm. Okay, our array should be sorted. Okay, and we already know that the time complexity for binary search algorithm is going to be of log n. Okay, so we are going to implement that algorithm here, and if you see, the constant size is very small. Okay, and this is an important property that nums is already sorted in increasing order, right? So here if you see, uh, total 3 negatives and 2 positives, so negatives count is greater, right? So I'm returning 3 here. All 4 are positive, I'm returning 4 here. Okay, so problem statement is very easy, right? And I hope that you guys are clear with the examples as well. Okay, now this is done. All right, so now here, first, before implementing the binary search on these examples, let's first understand what is this binary search algorithm. Okay, so let's read this. Okay, so binary search is defined as a searching algorithm, right, which is used in a sorted array by repeatedly dividing the search interval in half. Okay, so we are going to divide the search interval in half always. Okay, the idea of binary search is to use the information that array is sorted and reduce the time complexity of log n. Okay, I will show you how we are going to get the logarithmic and time complexity. Okay, so binary search is a versatile algorithm with numerous applications in various fields. Okay, so let's suppose you have very large data set. Okay, and in that large data set you want to search for any particular record. Okay, and you know that this column, okay, or is already sorted, so you can implement the binary search there to search for a particular record. Okay, this is one of the applications of this binary search, right? So here, see how this binary search algorithm works. All right, so here we are going to take two pointers. One is low, okay, and we are going to set this low at 0 index, and one pointer we are going to take high, and we are going to set this high in the last index. Okay, here high we are setting, and here we are setting low. Okay, now I told you guys to search 23 here. Okay, search for 23. Then what you guys are going to do, you are going to calculate the mid. Okay, so low is 0 and high is 9. Okay, so 0 plus 9 divided by 2, you are going to get 4. Okay, okay, 4 is the value that you are going to get. Okay, so let's take this 4 as mid. Okay, so now here you are getting m as 4, right? And at 4, if you see, you have 16, but you are searching for 23, right? But here we have 16. Now we know that we are searching for 23, and my 23 is greater than the 16. Okay, right now my m is at 4. Okay, so that simply means that I have to search in this window. Okay, that's the simple meaning of this. Okay, this, see, this value is 23, which is greater than 16, so that's mean we have to search in the second half. Okay, so now if I want to search in second half, then I'm going to update my low as, okay, this was the low initially. Okay, now I'm going to update this low as mid plus 1. So last time mid was 4, so I am going to update my low as 5 here. Mid plus 1, m is 4, 4 plus 1 5. Okay, so from here I'm going to search now, and this is the high. Okay, so low is 5. Okay, and my high is 9. Okay, divide by 2, so 14 divided by 2, you are going to get 7. Okay, so at 7, now your mid is 7. Again, you are getting 56, but we are searching for 23, right? So 23 is smaller than 56. That simply means that now I have to search in this window. Okay, in this window, right? Because my 23 is less than 56, so in this window. Okay, so now I'm going to update my high as mid minus 1. So mid was 7 last time, so now I'm taking it as 7 minus 1 as 6. Okay, so high is 6 and low is in 5 only. So now again 6 plus 5 11, 11 divided by 2, I'm going to get 5 as mid, and at 5 we have found that we have 23, right? So this is done. So in just 3 steps I got this 23. Okay, I don't need to go over all the elements one by one. Okay, so see, this is how my binary search algorithm works. Okay, clear? Now here the mathematical proof of getting of logarithmic n time complexity. Okay, so let's suppose you have n number of elements initially. Okay, then in each step of binary search you are reducing the problem size by half, right? Okay, so first you are taking this complete window, then you are checking where your element exists, in this half or in this half. Then let's suppose your element here, so you are going to search in this half then. Okay, so you are reducing the problem in half. Okay, so again you are going to get mid here, but you know that element is here, so you are going to search in this half. Okay, so each step of the binary search reduces the problem size by half. Okay, the number of elements left after each step. Okay, so in the step 1 n by 2, okay, we are dividing it in half. Then again n divided by 2, again we divide it with the 2, so we are going to get 2 raised to power 2, this is nothing but 4. Okay, that is 2 raised to power 4. Okay, then in the next step you are again going to divide it with 2. Okay, so n divided by 4 last time, again you are going to divide it with 2. Okay, so you are going to get n or 8, or I can write it n as 2 power 3. Okay, I can write it like this. Okay, again, so at step k, again 2 power k. Okay, so this is clear. Now the search stops when we reach one element. Okay, when we reach at that particular element, that let's suppose n divided by 2k, 2 power k. Okay, we have found that element is equal to 1. Okay, done. All right, now here 2k, we are going to take 2k this side, so this is the equation. Okay, rearranging the equation. Then here just write logarithmic to both the sides. Okay, 2k here, and here you can write log of 2n. Okay, and you can solve this part, right? So this is nothing but I can write it as log of k of log base 2 power 2. Okay, and you know that this value is nothing but 1 only. So here that is nothing but k. So k is equal to logarithmic of 2n. Okay, so here thus the number of steps taken by binary search is of log n. Okay, clear? So this is about binary search. Okay, so I hope that you guys are clear with this algorithm as well if you don't know about this. Okay, so now let's come to the problem, come back to this problem. Okay, so here let's take this example too. Okay, so -3 -2 -1, then two zeros, then 1 2. Okay, so here let's write this -3 -2 -1, two zeros, then we have 1, and then we have 2. Okay, now let's write the indexing for this: 0 1 2 3 4 5 and 6. Okay, and here the size of this array is 1 2 3 4 5 6 7 7. Okay, now here if you see, these zeros are neither positive nor negative, right? These zeros. So number of positive integers here are these. Okay, these two, right? And the number of negative integers are here. Okay, so these are nothing but my negative, and these are nothing but my positive. Okay, definitely you know the answer. Max the count of negative integers are 3. Okay, positive integers are 2. So the result is going to be 3 here. Okay, because negative numbers is greater, we have to return the max of neg and pos. Okay, so here if you see, output is 3. Okay, done. Now here see, just before 0, okay, just before 0, okay, we know that these elements are smaller. Okay, these small elements are smaller, these elements are smaller. Okay, and here if you see, uh, at this particular index, okay, at this particular index, this is the first element which is greater than 0. So if this is greater than 0, okay, then definitely this second one is also going to be greater than 0. Okay, we already know because our array is already sorted, right? Our array is already sorted. So here what I'm doing now, I am finding the first element which is greater than 0. Okay, so this is the first element which is greater than 0, right? This is the first element which is greater than 0. So here at index 5, so here I can write it like this now. So total size of my nums array is 7, and the first index where the my element is greater than 0, so that is nothing but 5 at 5 index. So 7 minus 5 is equal to 2. Okay, so let's say this is upper bound of nums, upper bound of nums. Okay, okay, so this upper bound of nums, this is a function that I'm going to write, and this function is going to give me an index at which we have the number which is greater than 0 for the very first time. Okay, so this is the functionality of upper bound nums. Okay, and now after that we have to calculate the lower bounds. Okay, so here I will search for this index, the index, okay, at which I have first 0 or some positive integer. Okay, the index at which I have first 0 or some positive integer. There may be some case where we have directly here some other value instead of 0, let's say some other positive value 3 4 5. Okay, maybe, right? So here I am searching for a first integer, okay, which is 0 or greater than 0. Okay, so I will name this as lower bound of nums. Let's say this function name is as lower bound of nums. Okay, and here I will just write the index at this particular position. So index at this particular position is 3. Okay, so this is nothing but my this negative value, this is nothing but my post value. So post value, to calculate this positive value, okay, positive count, nums dot length minus this upper bound of nums, and this upper bound nums is nothing but all integers from the first non-zero to the last will be positive. Okay, so this is for upper bound, and all integers from index 0, okay, to index before the first 0 index. Okay, to the index before the first 0 index. Okay, so they are going to be negative only, so here we have to just write 3. Okay, because we are starting from 0 now, so that is why we are simply writing this index. Okay, simply calculating this one only. Okay, done. Okay, so now here how we are going to solve this problem. Okay, so same logic that I have explained here. Okay, so now let's write the code, okay, step by step. So first let's write basic things, how we are going to get this positive count and negative count. Okay, we are going to just apply these formulas. Okay, and then I will write the code for upper bound of n and lower bound of n. Okay, but just first just make know that this upper bound of num is going to give me this index and this lower bound of num is going to give me this index. Okay, this we already know. Okay, and I'm going to write the code after that. Okay, so first let's write the basic code. Okay, so here first of all integers from the first non-zero to last will be positive integers, right? So here int positive count, okay, pc, or let's write it completely, positive count. Okay, so here that is nothing but nums dot length. Okay, and I told you guys that here we are going to call upper bound. Okay, and here I'm just going to pass nums. All right, now here after that we have to calculate the all integers from the index 0 to the index before the first 0 index will be negative. Okay, so here negative count, int negative count is equal to, just here write lower bound, and here I'm just going to pass nums. Okay, and we have to return what? We have to return math dot max of this positive count. Okay, let's just copy this, paste it here and here among these two. Okay, one second. Here negative count, that's it. Okay, this is done. This is what we need to return. Okay, this is done. Now let's write the code for let's start with upper bound first. Okay, so, all right, so here here I'm deciding to give the index. Okay, this is what I have decided here. I will give this index. Okay, so here I'm writing private int. Okay, return type should be int then. Okay, I'm returning the index, right? Upper bound. Okay, and inside this I'm just going to pass the nums array that I have. All right, and here inside this same start take it to 0 and end take it to nums dot length minus 1. Okay, so we are at this position. Okay, so nums dot length minus 1, that is 6. Okay, so this is my low and this is my high. Okay, start or end, okay, whatever you want to say. Done. Okay, now here take the index, initial index as nums dot length. Okay, done. Now here we have to calculate. Okay, so here while my start is less than equal to end. Okay, until then we have to execute this while loop. Okay, so here first we are going to calculate the mid. Okay, mid is equal to start plus end. Okay, and here divide it with 2. Done. Then we have to check. Okay, so what we are searching here, so we are searching the first number. Okay, we are searching for the numbers which are greater than 0. Okay, greater than 0. Okay, so this is what we are searching. So here I can write if nums of mid. Okay, if at nums of mid we have value less than equal to 0. Okay, okay, if at this particular index we have value less than equal to 0, that simply means, if this is the case, then that simply means that we have to search in the second window. Okay, so here in that case we have to update my start or low. Okay, you can say start or low, okay, whatever you want. So here in that case we have to update start as mid plus 1. But in case as if nums of mid, okay, if the nums of mid value, if it is greater than 0, okay, if it is greater than 0, then we have to check in the first half. Okay, so in order to check in the first half we have to update my end as mid minus 1. Okay, that I have already explained, right? And now here I will update my index. Okay, new value of index to mid. Okay, mid. All right, so and here from here I'm just simply going to return index. Okay, so this is done. Okay, for upper bound. Okay, so now let's see what is happening with this particular example. All right, so here let me take this color pencil. Okay, blue we haven't used here. Okay, so initially we are taking pointer as start and end. So, okay, so let me take those two only. Okay, so let's say my start is here and my end is here. Okay, so my start is at 0, my end is at 6, so 6 divided 2 I will get 3. Okay, so my mid is here. Okay, so now my mid is here. All right, so now I know I'm searching for the positive integers. Okay, I'm searching for the positive integers, so definitely I have to check in the second window. Okay, so my if my nums of mid is less than equal to 0, okay, is less than equal to 0, then start is updating as mid plus 1. So that is why my start is moving to this position. Okay, so this is new place of my start. Okay, start here. Okay, and in this window. All right, so let me just erase this. Okay, done. Now here my start is at 4 and my end is at 6, so 4 plus 6 divided by 2 I will get 5. Okay, so 5 is the new position of my mid. Okay, so here this is my new position of mid, so let me remove the old one. Okay, this one. Okay, so now here my nums of mid is greater than 0. Okay, if it is greater than 0, then I am going to search in the previous window. Okay, so end is updated as mid minus 1. So now here previously I have updated indexes mid as well. Okay, I have executed this part now, so I have updated indexes mid. So right now index value is 5. Okay, all right, now I am updating my end as mid minus 1, so my end is at this position. Okay, done. Okay, so my start and end both are at 4. 4 plus 4 divided by 2 I will get 8. Okay, so 4 by 4 divided by 2 I will get 4 only, right? So my start and end both are at 4 index, right? So here 4 plus 4 divided by 2 I will get 4 only, right? So at 4 my mid is at 4 now. Okay, so everything is at 4. Okay, so now here nums of mid is equal to 4, so my start is going to update as mid plus 1. Okay, so in the second half I am searching, so start is going to move to next position. So here my start is going to move to this. Now here my start crossed this end. Okay, so start is not less than equal to end, but my start is greater than end. Okay, so I have to stop. So last time my I was at 5. Okay, so this is what I have updated, so I am returning 5 here. Okay, for the upper bound. Clear? Okay, done. This is how we are getting the code, writing the code for upper bound. Done. Okay, now same way you have to copy this. Now you have to implement the lower bound. Okay, so here just change it to lower bound. Okay, so here again same thing. Okay, start we are going to 0 and nums dot length minus 1 and index is there. Okay, and here same logic, we are going to calculate the int. Okay, so here in this case we are finding the element, this element. Okay, 0, this is what we are calculating. Okay, so here if nums of mid is less than 0, okay, if it is less than 0, right, then we are going to search in the second half only. Okay, second half. So here I'm searching for start mid plus 1, but here instead if my nums of mid is greater than 0, okay, or equal to 0, greater than or equal to 0, because we are finding the first position of this. Okay, first position of this. So if this is the case, then I am updating my end as mid minus 1 and index is mid. Okay, then we are returning index. All right, so now let's run the code and see if there are any code issues. We'll try to fix that. Okay, so all the test cases has been accepted. Okay, and if you want to implement this, so let's implement this now. Okay, so here same array. Okay, let me take here. Okay, -3 -2 -1 0 0, and then we have 1 and 2. Okay, this is the array that we have. Okay, now I know that I'm searching for this particular index. Okay, this we know, right? 0 1 2 3. I want to see whether we are getting 3 as answer or not in this lower bound method that we have written here. Okay, so here first same start put here and put here, then you are going to get mid as okay, so this is right now. Okay, so you are going to get a mid here. Okay, mid here at 3. Okay, this is where you are going to get mid. Okay, so you are getting this 0, right, positive. Okay, so now I am saying that if your nums of mid is less than 0, so it is not less than 0, your nums of mid, Okay, right now this part will be executed. Okay, nums of mid greater than equal to 0. Okay, greater than equal to 0. So in that case, what you are updating, we are updating your end as mid minus 1. Okay, and as mid minus 1. So here right now what you are checking, you are checking that there may be some 0 here also. That could be the case, right? Okay, so there may be some other 0 here. Okay, so right now you are know that it is 0. Okay, but there may be some positive integer, so you are searching for the negative only, na? Negative only, or you are finding out the first 0, right? So here you are going to search in this window again, so your end is going to update to here. Okay, so your end is going to be mid minus 1. Okay, and here, and you are going to update your index as this value, okay, which is nothing but 3. Okay, you are executing this part. Okay, then after that again, um, here 0 and 2, so you are going to get 1. Okay, your mid is at this position, so you are going to get negative. Okay, so you are going to get a negative value. Okay, less than 0, so you are going to update as start as mid plus 1. So start is going to be updated to here. Okay, done. Then in the uh, next time if you see, your start is here. Okay, and is here, so again you are going to check mid, you are going to get mid here only. Okay, so this is also less than 0. Okay, less than 0, so again you are going to update start as mid plus 1. So start is going to jump here, so now start cross this end. Okay, so we have to stop. Okay, so initially we are just finding out that there may be some other positive integer, right? Maybe some other 0 in this particular example. Okay, or let's suppose there's a number like this 3 4 5 6 here, so you are searching, maybe here 2 is available, so that is why you are checking the first half, na? Right, clear? Now let's submit it. So see, our solution is accepted, right? And let's see the time complexity. So time compressor is of log n. Okay, so I hope that you guys are able to understand today's problem, and if you guys still have any doubts, then please feel free to ask in comment section. Till then, keep coding and keep practicing. Meet you guys in the next video. Thank you. Bye bye.